toy model that the number of scalar fields you had in the theory was for a very large number of species n. But each species is going to be radiated in Hawking emission. We know that. But I'm going to make it a very large number of species. Let m be the mass of the black hole. Let's say there are m over m Planck squared species. Of course, nothing realistic. I'm just playing around here. If you have that many species, what happens? Well, in any one species, first one quantum comes out, another quantum comes out. Hawking emission is a very, very long time process. But if you have so many species, of course, they're all coming out at the same time. And in fact, if n is bigger than this, the black hole never forms. By the time this shell comes in from 4m down to 3m, down to 2.5m, it's already lost all its energy to the radiation and just blown. Of course, we don't never take this seriously because we never have this many species, and even the number of species is normally fixed. So if you look at a black hole even bigger than that, but then again, this process shell will make a black hole, but it's just an initial toy model to set up the kind of calculation I want to do. Now we don't have that many number of massless species in string theory, but now we do have this many massive first-born states. There are other states we just showed which have a different topology where you come and you get pinched off. And the number of those is e to the s Bekenstein, e to the Bekenstein entropy. Let's compute the rate of going there. So normally when you actually have Hawking radiation, that can also be thought of as a tunneling process. There are calculations of this by Cross and Parikh and Wilczek which actually show you can think of this as a tunneling process. And if you don't worry about back reaction, the rate of process e to the minus omega pi t, like for any thermal system, t is 1 over 8 pi gm for the black hole, so you get a rate of radiation which goes like this. What Cross and Wilczek did was, they said suppose the energy being radiated is a good fraction of m, or at least not ignorable. You can actually compute the rate of radiation with back reaction, and it turns out that the m here should be replaced by m minus omega pi 2. So you can see a nonlinear effect is coming here. Is it temperature before radiation? Temperature after radiation, you take the mean, and that's how it actually was to be. And normally it would be a small correction because you radiate something of small mass. But anyway, you can apply this to radiation of any mass, and this formula is a special case of a general expression. Rate of radiation is the change in the Bekenstein entropy. So if you have the Bekenstein entropy of the black hole after it emits energy omega, and in the Bekenstein entropy before it emits that quantum, that difference, in fact, is the actual rate of radiation, now taking into account back reaction. Okay, this was a calculation lying around for about 10 years or so. But because it works for anything, what we want to do now is to ask for the amplitude for this collapsing shell to turn into a first-born state. We try to emit all the mass m at one go. If you now do that, if you put omega equal to m, if all the mass m is going to be emitted, for any one species of first-born, the answer is e to the minus s Bekenstein of m. So if you look at the previous formula, now for m minus omega is 0, so there are no mass or nothing here, only have to e to the minus s Bekenstein of m. As for any one species, this is the rate of radiation. If you the overall rate of tunneling to first position multiplied by the number of species, and the number of species e to the s Bekenstein, and the product exactly cancels.
Except that Cross and Wilczek's calculation would be valid if you said this large value.
No, it doesn't. It's actually exact. So you can actually radiate a shell which has mass, let's say m by 2, 3m by 2, and just taking it all the way to m. It was something done exact. They took radiation spherical shells. This is not the actual exact calculation of the entire gravitational constraint system of the shell, the Schwarzschild metric, and then solve all the constraints of gravity, and then complete on the amplitude. So it's not in the limit of omega being less than m. Omega can be anything. That's the limit. So omega much less than m has nothing to do.
So one question: the starting solution you have is a collapsing one,
Yes.
right?
Yes. Yes.
That, because this whole thing is a Euclidean decay process.
Yes.
How do you Euclideanize something that has dynamics in it?
Okay, good question. So I don't think of it as a Euclidean calculation right now, because Euclidean is just a trick, and you should apply that to something which is time independent. But in fact, most calculation of tunneling can actually be done with time dependence also. In fact, now even the bubble nucleation of cosmology is now done in a time dependent fashion. You can do it with the actual WKB wave functions, keeping Lorentzian signature. And that's the one I have in mind. And the Cross and Wilczek calculation actually goes like that. It's all in the Lorentzian section. And at some point you're doing an integral. At the final integral, you can evaluate by a starting point by going to the complex plane, but the calculation is actually in the Lorentzian section.
So we 10 minutes.
Okay, so here this is the calculation I was trying to talk about. And this is the mystery of how I think what was sort of missed about black holes all these years. We had this thing about the very large Bekenstein entropy being available, but we never knew what to do with it, because we never knew what to count it. But now we know what it counts because string theory can see all the states, there are exactly that many of them. They have no horizon, no singularity, but there are that many of them. And now they start intruding upon your classical physics, because if you do any quantum mechanical calculation, if you remember how path integrals go, there are always two terms. There's e to the minus classical action, and then there's a measure. And normally we don't worry about the measure very much, because the measure is a suppressed by a factor of h bar. So if you really want to do quantum effects, you look at the measure. Otherwise, you take the starting point of the action in the exponent, and that's how you do path integral physics for semi-classical things. But the entropy of a black hole, when worked on appropriate units, is exactly 1 over h bar. So the measure factor is no longer small. It's not order h bar, it's actually order 1 in some rough way of speaking. And that's why the entropy of the black hole is so much bigger than the entropy of normal matter. If you just see where all the Planck's constant go, the entropy of the black hole is big because it goes like 1 over h bar. And so in fact, this large measure factor is exactly the same order as we just saw as the classical action, the path integral. And so the entire black hole process is known as classical process. So as you start coming close to the horizon, there's so many alternative states in the full theory, all in this other topology, that you can't actually ignore them. Whenever there's an amplitude, there's some other possible states, there's some amplitude of wave function will spread in that direction. If there are too many of those directions, the wave function will spread a little bit into all of those, and the wave function will be gone from the place where you thought it was going. If you didn't have all those alternative directions, the collapsed shell would indeed go all the way to the center and make the singularity. So if you didn't have the extra dimensions, you didn't have string theory or any of those things, just had 3+1 canonically quantum gravity, useless shell would go in, you get a normal horizon, and you can actually prove that you have to go and get your remnants or information loss. But with string theory, that's not what we seem to be getting. And in fact, things change, and you actually get something else.
Are you describing the black hole like a Wittgenstein entropy to the Planck shell?
Can you say again?
Are you describing Wittgenstein entropy to the Planck shell?
Not the shell. So what happens is, the shell has very low entropy. When you make something on a matter, it is almost no entropy compared to the entropy of the black hole. But the number of things it can tunnel into, the number of these fuzzball states have the number of these is e to the s Wittgenstein. This many states you get for a solar black hole, there will be that many fuzzball states. So you have some amplitude to go to this, some amplitude to go to this, some amplitude to go to this. And because you multiply the number of these, that's the magic.
So, Samir,
Yes.
just as you get to the event horizon, then there is some sudden violation of this communication. That's
Right, the quantum effects take over. As you get near the event horizon, the quantum measure takes over, and the wave function starts spreading into these other directions. So that's exactly what's going on. So if you take a very simple example, if you're a particle moving in the x direction, you may ignore y and z. Okay. But you know the wave function slightly spreads in y and z as you go along. But if you make a very high energy wave packet, you don't really care. You basically go straight, like a billiard ball. That's why billiard balls go where they go. But suppose the number of directions were y, z, w, there were 1 million transverse directions. Actually, the wave function won't go like this. It will go like this and go like this. It's not actually going to go forward. And that's basically what is happening. If there's too many alternative directions, you can't actually ignore the quantum spread in those. And the large Wittgenstein entropy tells you that too many alternative directions in superspace, the space of all gravitational solutions, and that has blown your classical
so
approximation.
roughly how close you have to get to the event horizon before you would see a breakdown of it?
So we don't know the actual numbers that far. What I showed you here is the best we can do. We showed it's order 1. But order 1 means it can go down between 4m and 3m, it can go down between 3m and 2.001m. We just don't know the dynamics that well. The main technical work we do, these are the estimates. The technical work we do is we actually make these solutions with all of string theory. And what's remarkable is you really need all of string theory. If you make a single mistake with some number in string theory, like you miss a factor of 2, then you don't get these solutions. The things are either singular, they have naked singularity, or they collapse. But you get these completely smooth cigars and all the numbers string theory are put in exactly correctly. So I think string theory really wants to do this somehow. But if you try to tamper with it, instead of 10 compact dimensions, take 9, it's not going to work.
So in other words, there's no chance that we're inside the black hole.
There's no chance we're inside a black hole in the strict sense. But in fact, the last part I'm going to tell you is there any sense in which the inside can exist?
Right. I
So-
mean, and this, so this is one of the things you say with a very large black hole. You can
That's
never
right.
know because it's a teleological construction.
That's
You
right.
wait for all time before you know the black hole exists. But here you're saying
I'm saying
that you
no.
can locally tell that there's a black hole. before
Except for
you
what I'm
can
going to tell you now.
Okay.
So this is sort of the last part. Let me just take 5 minutes to say this. This is something which is very positive in the context of all this. Now suppose you have this surface. It looks like a bubble of nothing, there's nothing inside. You just have a surface like a membrane out there. Okay. So can there be any sense to which the Schwarzschild metric can be there, which we can talk about? The interior is such a beautiful metric, we don't want to completely lose it. But if we literally took that metric, we have the information paradox. Okay, so now we don't have the information paradox because we have this surface and the data comes off the surface. Is there any remnant, even effectively, of the old Schwarzschild metric? And I'm going to argue that there can be. So if you know that there's something called a membrane paradigm, this is what we have found. Horizon versus surface ends here, there's another part of space-time here, and so on. There's something called a membrane paradigm quite long ago, but if you take a normal black hole, but you put an imaginary surface out here, which can absorb and radiate stuff. Of course, there's nothing really there. But you can effectively describe all the physics of the outside. The boundary conditions on this membrane are such, it captures the fact that there was an inside. So if you haven't seen this before, that's okay. People who've seen this kind of logic, you can put some arbitrary cutoff and put appropriate boundary conditions to handle the fact you could really have the other side too. And it was this kind of picture called a membrane paradigm. So what it could be used for the electromagnetic fields, they really go outside and inside the horizon. But if you put this membrane, you put appropriate conductivity on the surface of the membrane, then the fields outside have just the right boundary conditions to behave exactly as if there were the fields on the exterior of a black hole spacetime. But that was just a picture which was helping people to do calculations, especially with magnetic fields near black hole horizons. But now we have a real membrane because the spacetime actually ended there. The surface of this bound of nothing. And the conjecture now would be that this real membrane has all the same properties, at least approximately, as this membrane of the membrane paradigm. So here's the conjecture of the first bond complementarity as we covered. If you take, let's say, a two-point function, a Green's function of two things near the surface of a black hole like out here, how will you compute this two-point function? If you're a normal black hole, you'll get a path integral with paths going outside the horizon, inside and outside, doing all these things, all part of spacetime. So all these virtual paths contribute to use both the outside and the inside. You can replace this by an effective membrane, and then you only use the outside, but then you have waves traveling on the surface of the membrane, and they basically account for the same physics. So you can account for the paths going in by actually not having any inside, but actually giving the surface a conductivity. So good stuff. But now the question is, can we get the same thing out of this actual real membrane where spacetime is really ended? So what you're really asking is, if you perturb this membrane by sticking two electron probes in it, it will have certain vibrations, and that will give you certain Green's function. If those Green's function are the same as what you would have gotten if there was no surface, but you had both sides of the horizon, then in fact you won't be able to tell the difference. Because the energy spectrum of something or the Green's function of something, they actually hold all the information of what you can ever measure in any quantum field theory. So this is the underlying idea that one is trying to get at the last part of this game. That whatever you can do, you can't actually fall into the surface, there's no place to go inside. But suppose you hit the surface, you excite vibration of this surface. There's a certain spectrum of those vibrations. In principle, you can compute them. There's also some spectrum to the normal traditional Schwarzschild hole for waves which are really falling in. You can solve the gravitational wave equation, you have a certain spectrum. Now, if the spectrum of radial infall into a black hole was the same as the spectrum of angular waves spreading on this actual surface we now have, you can't actually distinguish this surface from the black hole for almost any measurement. When the word almost comes in, the word almost comes in because there had to be an approximation. There were e to the s different possible fuzzball states, and they're all going to be a little bit different. How can they all go and mimic the Schwarzschild black hole? Well, of course, not really. When you probe the black hole with energies which are very low, of the order of the Hawking temperature, you see the differences between all the surfaces. On the other hand, when you probe its energies much higher than the Hawking temperature, which is easy to do, Hawking temperature is so very low. The radius of the wavelength of the Hawking radiation is 3 kilometers. Whenever you probe it with something falling in like myself, then its temperature energy is much higher, then in the limit E much bigger than T, these calculations are approximately the same as these calculations. So in fact, for anything heavy falling into the black hole, you don't actually notice anything. You don't actually go in. Your spectrum of infall gets converted to vibration, spectrum of vibration of the surface, but because spectrums are the same, in the limit E by T much bigger than 1, you can't actually tell the difference. Anyway, I just said this is much time and time to summarize. I'm putting up my last slide over here. So where should we go with all this? It seems that we now understand a lot about how black holes should work in string theory. There's no horizon, there's no singularity, the information puzzle is gone. People are making more and more of these states. It's been going on for about 10 or 15 years. We've never found anything which actually has a horizon. It's a well-defined theory, you can compute any state you want to any accuracy you want. We've never actually found any state which doesn't have this picture. So let's assume this is actually true for black holes and this is the solution of string theory takes for itself, the black hole information paradox. Does this actually help us to understand any other piece of physics in the world? When the black hole, we were basically compressing matter down to a point, at least classically, and now we see that doesn't happen. The whole thing actually was to blow up into this first of all and change physics on a macroscopic scale. But in the early universe also, if you go back towards the past, you're trying to crush matter all the way down to a point in case of the infinite density, and you want to know, is something different possibly going to happen there as well? And one question you can ask in particular is, in the limit of infinite density, does a well-defined theory like string theory have any prediction for the equation of state? And it turned out from many different points of view, it seems that it's a universal equation of state where the entropy density is proportional to root rho over g when you get to the limit of infinite density. Reading back to the past. So in fact, if this is true, and I'm happy to discuss with people if they are interested, then you can actually start bottom up for cosmology as well. If you know the equation of state you want in the far past, it seems to be pretty much unique as far as string theory is concerned, you can try to see where this guy would like to go, whether you have all these kinds of non-local effects that happen to non-local effects. There's nothing very non-local, but the big effects that come because of entropy. All these entropy factors. And it seems all the physics of these very early universe, this is much pre-equations, Planck's theory physics now. This should all be actually governed by these large measure factors. And that's what leads to this kind of equation of state. So there may be something very interesting to explore here, and we just started playing with this. I just stopped it. Thank you.
So we've had a lot of questions during the talk, so let's take a couple and then adjourn for lunch. Yes.
Two questions, but I will ask the first one first. To give an example, see, you're saying that entropy factor is very large. That is true for black holes.
Yes.
That is after the horizon is formed.
That's right.
So until horizon is formed, we don't have this very large entropy. Therefore, that argument cannot work. So let me put it this way: that in string theory, you have found microscopic states, etc., which have the property that as the coupling is increased, you get very large number of states. Entropy is actually larger. So you have got a model of black hole in string theory, such that entropy is large, even without invoking ever in horizon.
That's it.
Right? That's right.
That's
Now, but this calculation is done for extremal black holes with charges.
Extremal and near extremal.
Yeah, but we are extremal, but you can't take charge to zero.
We have taken charge to zero and gotten some states which are highly rotated. The angle of the A equal to 1 that we heard in the Ramesh's talk. If you put maximal rotation, it's sort of kind of an extremality also.
Yeah.
So you can have extremal but no charge.
But you can get that.
We made
So
microstates.
from microscopic state, you can
We have
the
made-
counting goes up to that.
There are no states in that limit because the activity goes to the limit of maximal rotation.
Okay.
This was fine with black hole. For what black hole we were working with, for those the activity goes to zero.
Then the question is like, okay, that is
Yeah.
one thing. So if that is the case, then at least you have a theory in which your microscopic distribution of black hole, which is consistent with Hawking radiation and entropy.
That's all I said. That's what it
So
is.
let me take another case where you start with the ordinary star which is collapsing. Okay, so that matter is ordinary matter. Now, as long as the radius of the star is just slightly outside the short-state radius, these extra states are no longer available. There are some normal matter which is collapsing.
Yeah,
Just
if you-
when R to process RH, suddenly these extra states become available at the horizon as well.
That's right. Yeah.
How does one understand?
Well, the states are actually not exactly at R equals to 1 because in fact the states are there everywhere. If for different masses you get, if I increase the mass, I'll have states here. Even larger mass will have states at these radii, right? So there are a lot of states in all different radii. The final on-shell states are at 2m if the mass was m. They're just at 2m plus a little bit, 2m plus epsilon. Right? So there's some transition probably to all these. And in the short-shell, let's just use any one quantum system. The short-shell quantum system is the best here because nothing actually goes inside. In the short-shell quantum system, we approach the horizon 2m asymptotically. You can come to 2.1m, but to go to 2.05m takes the same time as to go to half of that, go to the half of that. And every time you come one step closer, more and more of your wave function spills into these guys. So classically, you never actually get to 2m, but you know that was just a coordinate thing. You're not really following the thing all the way inside. But here, as you start coming closer and closer to the horizon, the wave function is not available in the shell anymore. It's actually already transitioned to these guys. So by the time you come to 2.0001m, by the time because the wave function has gone to these guys, in principle by the time you come all the way to 2m, all the wave functions gone away from these guys.
One question, but I will ask afterwards. Somebody else to get it.
So is your final state that you get, is that related to the hagedorn equation?
It's sort of an extension of hagedorn because as I was drawing this last slice, the hagedorn was something we realized in the early days of string theory when we only knew about strings. The entropy of the string state goes like S goes like E, the energy. Now for normal rotation, S goes like equal to 3/4. So S going like E was already a big thing for people, so we can get more thing than radiation. But in fact, we know that black holes have S going like E squared, M squared, right? So the question was, how do these things come? And with strings you can't make them because S goes like E. But in fact, if you take all these brains that we know about the strings right now, then you can get S going like E squared, which is like the black hole. So in fact, you have to use all the brains as well. So what this functional construction does is it actually uses all of non-portable string theory to actually make these guys. So in some sense, you can't do it just with strings. If you only had strings, then you have nowhere near the entropy you want. And that's why string theory has been around since the early 80s and so on, or even the late 70s. But itself, strings don't help you. It's only when deep brains came that really managed to get it.
Sorry, in the old picture, the deep brain configurations, black holes,
Yes.
string theory. Here, there are horizons.
That's right.
So, are you saying that those configurations are not direct descriptions
They are
of
not.
black
Yeah,
holes?
exactly. That's what happened. There was this very nice work of Strominger and Mathur, which was around the mid-90s, where they counted all the states at weak coupling in string theory. And then they counted the area of the normal black hole, and they found that the entropies are great. So that's very persuasive that there should be some states correspond to this. But I still thought the states at strong coupling looked like normal black holes, and weak coupling they look like strings. But as I was trying to draw here, that's not what actually happens. When technology became slightly better, you could actually follow the whole string state as the coupling increased. And that's what I was trying to draw here. At weak coupling, they look like this. But as you increase the coupling, you start getting this pinch off and the bubble of nothing kind of creations. And you actually end up going here, you won't end up going here. So what in the old days of string theory, Strominger and Mathur compared down of these to the area of this. But this still had a horizon for all the old information problems. But now the actual structure of what they were counting doesn't come like this. The actual structure is this. So now we have the structure of the states, Strominger and Mathur counting, and that's where the information paradox comes in.
Any questions from the back? If you can shout out.
So it seems like black hole horizon is a very special place for all observers within particle field. So
Yes.
this is that is its application to regular horizons or other horizons.
It is very interesting. There's actually a big difference, at least for the information issues. There's at least one difference between regular horizons and black holes. Sometimes people think that locally the black hole looks like a regular horizon, so it should be the same. And then you get into all these puzzles. But actually there's a big difference because Rindler is m equal to 0, there's no mass there. The black hole looks like Rindler in the limit n goes to infinity, when the black horizon becomes so big that locally it looks flat. These are very opposite limits. But if you look locally, you can't see any difference. But if you look at exactly the kind of thing we solved the problem here, it was the number of states being e to the m squared. That is why entropy is m squared. So you see, in Rindler there are more real states there. But with the e to the m squared, that measure factor is completely different in the m equal to 0 limit and the n goes to infinity limit. So because people took the classical limit first and said locally the black hole has to look like the horizon, actually then one can prove there's no solution to the problem. Part of the stuff which I didn't talk about here is now you can prove that Hawking's argument is completely stable, very small correction, very big. Okay, if you don't actually have some breakdown of the no-hair theorem, you actually can't solve the problem. So you had to find no-hair one way or the other.
Last question, Shrikant.
My question is related to one of Shyam's regarding core collapse of a star. So there initially you have a matter distributed on the curves, so mu and r equals 0 in regions inside what would eventually turn into a event.
Yes. Okay,
So when the collapse actually proceeds to form a black hole, what happens to the matter energy?
That's a very good question. I don't think we know all the details of the dynamical process at this time. But once the spongles start forming, you start turning into these new states. So that all the information which was there inside the thing which was trapped inside, it all gets sucked into what is happening outside. Because you could then ask the same question first in the toy model which I just gave you. So we have this toy model where if you have a large number of particle species, if I just have a shell, the shell blows off before reaching here. So this is, I think, something people really believe in. You can start with somebody sitting in the center, and then the shell was coming, and then the whole thing blows off. But when it blows off like this, there was some time in between where this mass plus the mass in here together created this whole blow off. As you can see how the data of these guys will actually have to capture the information of this also. So what do you do here? With large number of master species, in some sense now you're doing with the massive species, the same thing is working. Okay, the number of massive species keeps growing with the end, that's the whole point. But You can just play with the toy ball that the master species artificially set to M1 and pi squared. And whatever philosophy you get here should be really different from the philosophy you get there. But we don't know too much more about that. This is a little bit where we are right now.
We're eating into the time set aside for lunch, so let's clap for speakers. Last announcement by Sumit.
Yeah, just so that you can get to lunch. Lunch is in that corner above the library, right at the terrace. For those of you who have trouble walking or climbing stairs, take the elevator, but you have one last flight of stairs to climb. And please, those of you who are presenting posters, run and put your posters up, because all of us will come and ask you questions during lunch.